Good morning. Welcome to the live webinar, Practical Considerations for Force Limiter Vibration. This webinar will be recorded and a link will be provided in our follow-up mails to the attendees. Also, attendees will be muted, so please use the chat to ask questions. And at the end of the webinar, we will cover the questions. Both Dale and myself, I'm Bill Zwolinski, are application engineers with many years experience helping customers solve testing problems. So now, without any further introductory comments, we will proceed with the webinar. So what our agenda is for today is we're going to talk basically on force instrumentation topics, covering why force limiter vibration, some practical considerations of installation, mounting, and using forces and moments in a force limiter vibration test. And M+P will talk more on the vibration control topics, external and software summing, force limited configurations, notching, and also a live force limiter vibration demo. And at the end, we'll wrap up with our questions. So it's always good to start you just as a perspective as to the life of a satellite, from launch to deployment. This diagram was in an article that I read some time ago, and I felt it really did a good job, highlighting the high levels of vibrations and shocks over the duration of that flight. Obviously, it's very important with regard to environmental testing to ensure that the satellite survives and operates after launch and deployment, which is the main focus for a lot of what we're doing from the environmental test perspective. I mean, such testing includes subsystems, components, and spacecrafts and payloads. Certainly vibration testing, everything from sign, random, and transient, could be modal analysis, force limiter vibration, shock testing, vibroacoustics, electromagnetic testing, and also thermal vac testing as well. Just as an example of what type of acceleration forces that could be present during launch and flight, you can see on the two plots to the left, anyway, that the GLASS mission was specially instrumented to really get some useful data just at how are these accelerations and forces really, what magnitudes are they? And you can see on the acceleration, there are some fairly higher level peaks on the lower frequencies. Certainly on the, you can see the first axial mode on the spacecraft around 32 hertz on the force perspective, around almost 23 kilonewtons. And the lower frequencies are caused mainly by the launch vehicle. So it just gives you a perspective as to that there are considerable levels of acceleration and force during launch and flight. So the classical vibration test problem is that the dotted lines are the in-flight acceleration at the interface, and what you try to do is you try to control the vibration between those levels. A standard vibration controller, because of the load anti-resonance, a standard vibration controller would increase the shaker output, resulting in overtesting. And that overtesting can be up to, say, 20 dB. So force limiter vibration testing helps solve this problem by reducing those levels considerably. There's a large difference in mechanical impedance between the flight mounting and the vibration test mounting. And that's a highlight of the benefit of force limiter vibration. This here shows an illustration of how it might look in terms of real operation. You have a slip table, shaker, and you have here a test article, and you see a ring with force sensors underneath, and that's just showing how you're instrumenting the fixed base of the payload, and you're trying to detect the fixed base resonances to be able to implement your control algorithm. As you can see, there's many different parts of the implementation, from force sensors to shakers to signal conditioners and so forth. So again, the block diagram would be a test article on shaker, force sensors with accelerometers, shaker control, data acquisition, and vibration controller, as well as sensor and signal conditioning. What force limiting really is aiming at doing is replicate the test article resonant response for the actual flight mounting condition. Flight equipment is typically mounted in a relatively lightweight structure, so which mechanical impedance is comparable to that of the mounted equipment. Shakers have extremely high, infinite or nearly infinite mechanical impedance, so you're trying to take that into account with force limited vibration. So traditional vibration, as I said, controls on the input acceleration to the frequency envelope, and that does require a considerable amount of analysis. We're alternately limiting the input force at the fixed base resonances of the unit under test is less dependent analytically and provides an automatic notching with regard to over-testing. The implementation of the actual control is an extremal control, where conceptually frequencies other than the test item resonances, the acceleration test specification usually controls the test level. But when you're at the test item resonances, the base reaction forces are increased, and that's where you want to implement the force limited vibration control. This is an example of what you might find in actual practice, where the diagram showing an unlimited input force, and basically this notching that we just talked about. And Dale will go into it in great detail. Basically, prevents a over testing of that satellite due to that resonance condition. So we're going to go into now some discussion on the piezoelectric instrumentation. We're going to focus mainly on force sensors, but you see a 3-component force sensor here. What we mean by 3-component force is that it measures X, Y, and Z, and then that's integrated into could be a dynamometer or a force dynamometer, and we'll talk about that as well. So there's terminology with piezoelectrics, PE and IEPE. IEPE means integrated electronics piezoelectric. This means that there's an electronics inside the sensor, so that you're basically limited. You have a fixed range, and you're basically a dynamic sensor at that point. With piezoelectric, on the other hand, your electronics is outside the sensor, and it consists of a charge amplifier. And what it does is allows you to range the measuring chain to your specific levels to get the maximum utilization of the dynamic range. And it also permits a quasi-static operation, which allows you to do functions such as preloading and setup of the vibration fixture. Obviously, with this type of setup, there's a reset measure operation, so any static mass is really teared out in terms of the dynamics. So what I'd like to show here is that the piezoelectric sensor is typically viewed as a lightly damped second-order system on the high end and a single-order high-pass characteristic on the low end. Because of that, you can write some closed-form expressions with regard to amplitude response. So if you know what your vibration fixture supports in terms of natural frequency, you can estimate the 5%, 10%, and 3 dB amplitude response by Fn over 5, Fn over 3, or Fn over 2, respectively. That's often helpful to understand, the quality of your vibration fixture, and does it accommodate the frequencies of interest that you want to be able to measure and control. So charge amps, we showed a diagram earlier of an external charge amp. They can look in many ways as the desktop feature, or maybe a rack mountable multi-channel charge amp. But what's really important with charge amps is often what range they can operate on. The unit of output of a piezoelectric sensor is picocoulombs. So the minimum and maximum range are often important in having a lot of flexibility in measuring from different payloads and different sizes of payloads, and this gives you some flexibility in the end. So low frequency, I'm not going to go over this in detail, but we're going to these slides will be available. Basically, the low frequency is as I said, a high single order high pass characteristic. So this is range dependent. So depending on the range that you're selecting, measurement range, you're going to have a certain low frequency characteristic. So just keep it in mind that there is a terminology called time constant, and that's related basically to a high pass filter. And the closed form expression of a high pass filter is the 5 and 10% 3 dB amplitude responses are shown there. Quasi-static and dynamic measurement. A quasi-static amp or a dynamic amp is just doing that. It's measuring dynamic signals, swept signs, transient responses, and so forth. It's not very good at measuring quasi-static or static signals, whereas a quasi-static charge amp is, and it can measure all those, both dynamic and static. Why we talk quasi-static is in the preloading operations of multi-component force sensors. We're going to go over that shortly. So I mentioned rangeability, and what I wanted to show here with a piezoelectric sensor, that you might have a 10 kilonewton sensor with a certain noise floor if you operated it at full scale. But as you range it down, even to here to 1 Newton, you would get a reciprocal benefit of noise. So it actually, you actually improve your noise floor as you range the sensor. So it really provides a lot of robustness, and it gives you the ability to have almost a universal test capability that can be accommodated to your needs. Also on the front end there's also other amplifiers, charge amplifiers, and without going into great detail here, these are both very capable charge amplifiers, both quasi-static and dynamic, but also integrated data acquisition systems on top. So in some cases, it might be useful during a force limited test to have a backup data recording as well. So that certainly is an option with some charge amplifiers that are on the market. So now we're going to go into force dynamometers, and what a force dynamometer is it's really a you can think of it as two parallel plates with force sensors mounted in between. So it's basically a sandwich construction. Those force sensors, in the case of force limited vibration, there are 3 component force sensors, as I mentioned. And basically, you can take many of these, or in this case, 4 of these 3 component force sensors, mount them into under a top and bottom plate, and get a force dynamometer. And we'll show you a little bit more on that. But basically, the use of dynamometers is really, it allows you to absorb the moment loads by differential force reactions within the sensor array. If you have an object just on a single sensor, you can absolutely get very poor measurements, and actually could even break the sensor due to bending loads. So what the dynamometer does is allows you to take a large object that you cannot really mount axially and really distribute those loads amongst an array of sensors to derive the forces and moments associated with that event. There's also analog bandwidth considerations in every problem. It gets in the fixture design primarily, but you want to always take care in looking at the stiffness of the sensor, the stiffness of your top and bottom plates, and really look at what the natural frequencies would be and what your operating frequency would be with a given mass in mind. So this is all part of putting together a vibration fixture and making sure that it actually accommodates the mission or the test goals of the vibration test. Just to show quickly what force sensors might look like, these are 3 component force sensors. They have obviously different load handling capabilities. What I wanted to show here is just simply there's different stiffnesses as you go from small or low level sensors to higher level sensors. The sensitivity is roughly similar, in some cases, but what you see is a real increase of stiffness. So for higher load handling applications, you have also the benefit of even a much stiffer sensor, which gives you a higher natural frequencies in general. With force links, these are already preloaded at the factory. This is what it might look like. So the installation is simplified, but the thing to note is that the height of that is usually 2 to 3 times that of a sensor, the sensor alone, and also the stiffness comes down due to the top and bottom flanges. So you can see that here in the tables that for this sensor here, you had like a 4,000 newtons per micrometer stiffness in the axial, and if you go back here, it's nearly double. So a lot of folks in the force limiting arena still use the individual force sensors, go through the actual preloading and installation operations, which we'll talk about shortly. So this is what a dynamometer looks like. It's basically a square dynamometer or a rectangular one. So you have 4 sensors. Each sensor has 3 outputs. In this concept here, we have 12 signals, but internal to the dynamometer, we pre-sum X and Y, and that's shown here by the yellow and the blue, and the red signals are all Z, and in that case, you're left with 8 signals on the output. Well, with that in mind, you can write the closed form expressions for forces and moments, giving you a 6-component capability just by using 4 3-component load cells. This is sort of a schematic of how you would go about figuring out these equations. So you basically know what the X, Y, and Z axes are. You group sensors in groups of 2, and you basically compute and you have the moment arm A and B. A is the vertical separation, and B is the horizontal separation to center. And then you use those parameters to really write the expressions directly. And it's pretty straightforward. So some basic guidelines and multi-component force basics. With any dynamometer installation, you want make sure your load-bearing surfaces are properly configured. You want parallelism and flatness at a good level. You want also strength of materials. A lot of times, hardened aluminum is used. That's quite common, but steel might be used as well. Certainly, you don't want a flexing or a lack of stiffness in the top and bottom plate, because that could add to bending moments in the sensors. You also want, with preloading, we talked about earlier, preloading is used for 3 reasons. 3 reasons. One is to get a optimized linearity, to provide compressive and tensile force, symmetric tensile and compressive force, and the shear force handling is basically 0.2 times which is the frictional coefficient of the force sensor, times the preload force. So the preload operation is very critical to linearity, to compressive and tensile force handling, as well as shear force handling capabilities. So it's one of these operations that we really give a lot of guidance on. We really help customers implement that in a good way. We'll go into that just briefly shortly. Linearity, again, is simply just the input versus output plotted on a curve through 0, and then you look at the deviation from that curve to the points taken, and that gives you a measure of linearity. A lot of times with piezoelectric sensors, you can do partial range calibration, and that gives you, here in this case here, this sensor was almost a 0.5% linear at full scale range. But if you go to maybe a 10% range, you're at 0.13% linearity. So you can optimize your linearity just by doing partial range calibrations, which might fit with some of your the payload measurement ranges that you would need. We have also preloading acts as a shunt. It's in parallel with the sensor. So basically, you're expecting about a 6 to 9% reduction of sensitivity by preloading. That's very common, and it's very important to pick the right preloading bolt. If you pick something too stiff, the forces will go through the preload bolt rather than the sensor. I talked about tensile and compressive forces. You want a good preload of 70%. And what this gives you is if you preload at say 2/3 the measuring range, you get plus or minus 1/3 of the tensile and compressive range. That's the basic concept behind preloading at a high level. Also, sensor alignment is very important as well, because every 1 degree misalignment, it relates to about a 2% crosstalk in X and Y. And crosstalk is also on data sheets and also calibration certs. And calibration certs often show, they show the actual crosstalk, but it's also usually quite a bit better than what might be in a data sheet. The data sheet is a maximum value. The calibration cert is the actual value. Anyway, to align, you often use cylindrical pins around the connector, or in this case, this situation basically built a fixture with the ability to actually press against the flats of the sensor to keep everything aligned. And at the end, once these sensors were preloaded, these fixtures were just unscrewed, and they were basically no longer part of the vibration fixture. So many ways to preload, but I like this latter case. It really is a cleaner approach, and it just takes a little care in the fixture design. This is just an example of preloading of a dynamometer. What you want to do is you want to use a star pattern, and what I often suggest to all folks is really do like a 25% increments. Okay, so you break it up, in this case 16 steps at 25% increments, and you're able to then get a check mark or initial after each preload step, and that way you ensure that you've preloaded fully. It gives and it also gives a record that it was preloaded in a proper manner. So I really encourage some sort of a checklist or sheet that accompanies a preload operation to ensure everything was done properly. I talked about dynamometers before. It's basically a spring mass system, and all I wanted to say here is that as you add mass of your test article, although you can reset operate and take that out of the electrical response, it's still there structurally and mechanically. So what happens is you get a reduction of natural frequency with mass, and that's given by just a standard spring mass model, as you see on the right. This is an example of a test that was done at NASA some years ago, but basically it's an observatory with substantial mass using 12 sensors in a ring configuration, and the preloads were quite high, and they were done in 25% increments, and there was a custom bolt being used instead of a standard bolt from Kistler in this case. This is what it might look like schematically, okay, and how you would write these expressions of forces and moments. You'd apply the same type of rule that I applied on the rectangular case earlier. So as you can see, the moment expressions get fairly complex, but the good news is a lot of the advanced controllers, such as the M+P, VibRunner, calculate all these in real time, these forces and moments, and you just need to put in the geometry, and then you get real-time calculations. So it's really cool nowadays to have such advanced capabilities in the controller side. Force ring preload, I just want to show what it looks like. You lay the sensors down. You're obviously putting the top plate on and then doing the preload operation. As I indicated earlier, you have the shunt effect where you're getting a lower sensitivity. But after you have this all put together, we're going to also have to calibrate the vibe fixture. And how is that done? So how that done is really due to measuring the apparent mass. using force and acceleration in the direction of the vibration. And you compare that against the mass of the the mass of the fixture itself acting upon the force sensors. So this vibration test is done either as a low-level sweep or a dwell below the first resonance. And here you can get a comparison of the apparent mass versus the actual mass, and then work out a calibration factor. And usually these come out to be fairly close. So within a couple percent, I usually don't worry too much about that. But if they're off by 5 and 10%, there's usually something else going on. Maybe a sensor is bad, a cable is bad, and these are where you want to do some troubleshooting. This is what it might look like in terms of a force limit vibration test with these dynamic amplifiers we talked about, where you have the M+P shaker controller vibe runner. You would have several sensors going through dynamic amps and then through also quasi-static amps to do the pre-summing function. And Dale will talk about that in a little more detail. And at that point, I'm going to throw it over to Dale, and I'll stop sharing here. Dale, it's all yours.
Thanks, Bill. It's really good information about those force sensors, and I can definitely attest that the preload operation is extremely important. And I thought it was worth taking a look at that, so we'll take a look at that operation in just a little bit. Let's see. I'm going to share my screen here. Can everybody see this?
Yeah.
Okay. This is just the force sensors that I have set up here. So I'm going to get back to. There's the whole presentation, really fast. That's it. So yeah, thanks for tuning in to this webinar. We're going to go through this agenda here. But first, if you remember back to the invitation that you got in the email or on the landing page of registering for this webinar, this lovely giant 30-something force washer setup here. This is an example in marketing versus reality, because what you're going to end up with is this tiny little CubeSat behind me that we'll be testing, because, well, frankly, this fits in my office and that doesn't. So without further ado, I'll go into the agenda here. In the first part of this webinar, this portion of it, I'm going to go through external and software summing options. We're going to explore example force limiting configurations. We're going to talk about notching techniques, including manual and automatic notching comparisons. Then we're going to look at an overview of our demonstration configured, followed by the live demonstration itself. We're going to review the data collected from the live demonstration a little bit, and then we'll switch over and answer some questions. So in this part, we're going to compare external summation, or summing with external hardware, and then compare that with software summation. External summing utilizes charge amplifiers and summing junctions to reduce control system channel utilization. In this configuration, each axis is summed, providing combined output channel for each axis. Additionally, pairs of force sensors can be combined to calculate in-axis overturning moment. So these two force sensors, each in each pair, are used to calculate the force moment about the datum. And then those resulting summed forces can be sent to the control system for limiting functions to be applied down here. So all of these cables essentially get driven into their respective summing junctions, or in those force expressions that Bill had mentioned before, are used to calculate in an external hardware box. So this could be one of the Kistler models. In this example, I have the 5017B, but there's quite a few more that do this. Then those resulting signals get sent to the control system. So for this example configuration, we've only used 4 channels, one for force X, force Y, force Z, and then moment about the X and Y. External summing has the advantage of providing an independent hardware solution, so this uses less control channels. However, the increased complexities can lead to more failure points, and individual cables must be independently verified before the test. Now, if we use software summing, on the other hand, each individual channel is passed through the charge amplifier directly to the control system. As a result, individual channel limits may be applied to each axis and each cable, or each portion of the force sensor. Because the software calculates the overturning moment for each sensor instead of in groups, off-vector moments can be captured. So if there's any center of gravity offset on the test article, this will get captured and it will limit. Though this solution requires more hardware channels and is calculated by the same system providing control of the shaker table, it offers numerous benefits. Firstly, the moment calculation system can be configured with just the Cartesian coordinates of the sensors, greatly reducing complexity. Secondly, pseudo-channels are used for calculation and are only limited by the software, so groups of sensors can be summed separately. Lastly, the individual channel limits can warn the user if a bad cable or sensor occurs. And this does happen. In fact, in my very original testing of this type of configuration, we noticed that one of the channels was bad. And you can see this down here. And it happened to be one of the force sensors that wasn't directly in the center of the moment datum. It was more toward the side. But it did bring the overall average of the in-axis force down a bit. And as a result, if we were to limit to this particular force, we would actually be limiting to a lower value than is actually being captured by the system. So this can lead to overtesting if not caught. Now we can go ahead and review the various software configurations available for the force sensors. In the control software, there are 3 options for pseudo-channels. The first is root sum square, or RSS, in the software. This allows 3 axis sensors to be mounted at off angles, and it'll quantify the total energy of the sensor using a simple calculation here. Summed force, which is known as vector add in the software, is a simple weighted sum of all the sensors in the calculation. Moment, which calculates the overturning moment of a system using coordinates or weighted by distance, is calculated using the force expressions that Bill had mentioned earlier. One critical component of force washer installation is preloading, which requires precise application of torque in segments to arrive at the correct preload. For this, the quasi-static charge amplifiers must be used with a long time constant. And this is in our system behind me. I did do this, and we'll show you this in the photos in a moment. Some of the charge amplifiers can be directly controlled by this control system via USB connections, so that these sensitivities, the preload sensitivity and the operational sensitivity, can be entered directly in the channels table of the control system. Just as important as correct preload are installation locations and orientation. As forces are summed in the time domain, opposing polarity can lead to signal cancellation. So the polarity is very important when installing. However, if you're doing software summation, if the polarity is reversed, we can reverse it in the software by entering a negative sensitivity. So this is the summed force operation in the software. You can see that we're utilizing the vector add feature with a weighting of 1 per channel. So this is just a simple summed force. And here are the 4 channels in the Y direction. And a limiting or notching profile can be entered with multiple breakpoints on top of this particular channel operation. And this operation can be done for all axes if you're using software summing. For single plane overturning moment, or moment only in the axis of motion, vector add calculation can be applied. But instead of weighting with 1, we actually use the weighting of based on the distances from the moment datum. And this can give you calculated moment in the direction of excitation. To automatically calculate overturning moment for any vector of motion, the moment channel calculation is used. For this, you must enter the Cartesian coordinates about the center for the mode, but the limiting function will be applied to the true overturning moment of the system. Prior to force-limited vibration testing, engineers had to limit the force input by using a manual notch or shaped input profile. Here we'll look at this type of technique of manual notching and compare it to the automatic method. So manual notching uses predicted or measured system response, or essentially like a low-level sine sweep before the test, to change the reference profile. This is sometimes known as a bathtub notch due to its shape, and it requires less equipment to execute. Defining the notch requires careful analysis of the system response. In our example specimen behind me, we have made a low-level sine sweep to determine the forces that would occur at higher level tests. A properly designed manual notch should be somewhat follow the slope of the response Q factor, which you can see here on the first and second mode. Notice on these green dotted lines that the force imparted by the input system starts to diverge on the input force as it leaves the rigid body mode. So down here between 20 hertz and say about 300 hertz is the rigid body mode where everything is moving together. And then where it starts to diverge is where we should probably consider starting our initial slope for the manual notch. Where the blue dotted lines appear is where we will flatten the bathtub to its lowest level. To determine the level, I've simply taken the ratio of the desired response, which is 2 pounds force, which is what we're going to attempt to limit this to in the live demo, and applied that ratio to the actual response, which is 6.78 pounds force, and that's applied to the input force. So for the first mode, based on our calculations, the value drops from 0.1 G at the first part of the bathtub to 0.029 G. The second mode doesn't require as much reduction, but it ends up at 0.0438 G. This has a more aggressive slope, however, so this more aggressive slope due to the lowly damped Q is applied here. When defining an automatic notch, on the other hand, much less pre-test analysis is necessary to determine those limit values. Though easier, it's more critical that the sensor configuration is rock solid, as it's heavily relied on to produce these results. With a fully automatic force or moment limiting notch, the acceleration plot remains undisturbed, as the system will attenuate the input acceleration to limit the force. So you can see that when we do this automatic notch testing, we're going to have a flat response at 0.1 G all the way across. The force limit can be simple, like the one seen here in the notch profile, or really complex to account for various modes of different values. These two techniques can even be combined to help catch deficiencies in the manual notch or as a safety net in the case the automatic notch fails. Combining the two, however, can lead to test aborts, as the handoff from one to the other is often rather abrupt, and we'll see this in the live demonstration. And here we will review that configuration. So our setup consists of CubeSat. This is a mass mockup of a CubeSat. It's not a real one. We have an IEPE control accelerometer with a sensitivity of 100 millivolts per G, as well as a response accelerometer on the top, which has a 10 millivolt per G sensitivity. These are both IEPE. We have a force ring, which provides a platform for the test article atop the force washers and gives us the ability to preload. We have 4 force sensors here. These are the 9028C by Kistler. And then we have an expander head, which is meant to increase the size of the armature. So the force washer orientation is as shown. So the Z-axis is being normal to the shaker, and this is what we'll use to calculate the overturning moment. The preload bolts with threaded nuts make installation much easier. I didn't have these here, and I do plan to modify the fixture in the future to accommodate for those, because frankly, having the preload bolts with a threaded preload nut on top really simplifies the installation, because if you can imagine putting this plate on top of the force washers, you have to load the bolt from the top, which is really inconvenient. If you have the preload bolts with the integrated bushings, not only does it electrically isolate it, but it keeps everything aligned with in terms of the force washer, so that you can set the plate on top. Now our LabAmp configuration has all the force X components here, all the force Y components here, and all the force Z components here. These outputs are then scaled 1-to-1 as the inputs controlled, or as the inputs are wired directly to the control hardware here. And as mentioned before, the Z-axis charge amplifier is capable of defining a long time constant, which is set on this charge amp, in order to properly apply preload. So let's run a test. I have here a pre-signature sign sweep that I've used. And we're going to start off with the manual notch. So I'm going to start this in our profile. This is going to run through and do a self-check, which essentially puts a pseudo-random signal to the shaker. And this pseudo-random signal is averaged across the channels to actually make some predictions about how the test is going to run. So even before I've run, I can see my in-axis response is predicted to have these very specific modes. And you can see my 2 bathtub notches, so to speak, or manual notches. And as I start to run, we can essentially do a really quick in situ calibration. We're in the rigid body mode, and I know I have about 8.5 pounds of hardware on top of those force washers. So as I'm holding the test here, I have the in-axis force divided by the control channel input, which is 0.1 Gs. So even though I'm only reading about 0.8 G, or 0.8 pounds force on the summed in-axis force, if I divide that into the control channel and do a transfer function, I can actually derive the actual mass. So if I were running this test at 1 G, I would see that I have about 8.5 pounds. So I'm going to unhold it here, and we're going to continue our sweep. Now, one important thing to look at here is the in-axis response. We need to watch our in-axis force here because we're attempting with this manual notch to limit to 2 pounds. But you can see I kind of underdid it because the damping response was not taken into account when I calculated this manual bathtub here. So here we're continuing our sweep. You can see we went through the first and second mode, and there's a little bit of control here. And we have a third mode here that we were not able to control because we never really accounted for it. And this kind of illustrates the importance of the pre-test analysis. If this third mode happened to appear at a part where my FEM did not expect it to be, and I had only drawn my notch up to that point, then this would be a real test abort. This would happen on your test article, and it'd be followed by meetings where everyone's discussing what happened. And this is the importance of drawing that automatic notching all the way across your profile. So here we're going to switch over to an auto notch. I'm going to open this here. Running through the same self-check operation to do our predictions. And on this one, you're going to see the in-axis force actually has a notch drawn across at 2 pounds force. So as I begin to run, you can see our profile is built flat. We have 0.1 G all the way across. And what I was expected to see is that as this in-axis force approaches 2 pounds, this notch should kick in and relinquish control from the control accelerometer over to the in-axis force. Now I could have also set this on moment, and someone earlier had mentioned cross-axis response. I could also limit on the cross-axis response, but it's important to note that the control system can only limit off of one channel or one maximum error at a time. So whichever one contains the maximum error will take precedent. You can see my cross-axis response here. Here's the cross-axis X in light green and the cross-axis Y in green. And these cross-axis responses toward the mode do get close to the input profile as far as the 0.1 Gs is concerned. Now notice this test, because I drew this manual notch, or this automatic notch rather, all the way across the n-axis force, it predicted and accounted for the third mode. And even though my analysis was poor and I didn't predict it, this automatic notch did. So it caught it. You can imagine if this were a real test article, what would happen here if you predicted the third mode at some other frequency other than the 1492 hertz that it did peak at, and you drew the notch only at the predicted frequency, you could miss it and damage the test article. So as I mentioned before, you may be tempted to try to combine the notches for this. And I've seen this happen in the real world, and it can work. And what we're taking is my manual notch here, which I've defined earlier, and I've applied the automatic notch as well. So this is using both techniques. Okay, we're going to run this one. And I've started at, typically you can start these sweeps, much lower. If you have larger structures, you're probably going to start the sweep at about 5 hertz or so to capture some of those lower modes, as these larger structures tend to have modes, down in the teens, 15, 16 hertz or so. So here's our manual notch, and notice right here at this portion, it did kick in on the in-axis force because, like I said, my manual notch didn't account for the damping. And this is where that handoff happened. Right about this point here at 530 hertz is where it handed off the control to the in-axis force. And you can see that right here. Now, one advantage to doing this combined notch is that although my manual analysis of the 2 bathtubs that I defined was effective at reducing the input, this one that I did not predict over here was effectively captured by the in-axis force response and its notching. Now, how can I compare these two? So I've got this comparison here. This is the automatic notch in blue, which we had run as our second run. The manual notch in red, which was our first. And then I've kind of shaded the areas here that were either under or over tested as a result of using the manual notch. So because our approach did not properly follow the quality factor of the input force response, which is essentially inherent to the impedance of the system that we're testing. So this, not only the CubeSat itself for the test article, but also the force ring on top, the stiffness of how the two are connected, so that's a boundary condition. All of those play into this inherent stiffness and these resonances. Now the blue areas are where this was under tested by the manual notch, and the red area is where we over tested by the manual notch and even encountered a test abort. This is the same test comparison, but with force. So this is the in-axis force, and you can see where our automatic notch. So these areas here were somewhat under tested with respect to the test specification, and this area here was grossly over tested. You can also see this in the response. So this is the accelerometer that is mounted to the very top of this test article. You can see that even the response here follows this manual notch. However, there were areas that were under tested by the manual notch. You can see those here. So this is basically our live demonstration. I'd like to open it up to any questions that you may have. And yeah, thanks for listening.
Dale,
I'm just going to stop sharing here. I do see a couple of questions. Sorry, I was trying to get back to the chat window. Yeah. Okay. So the first one was, can we give any recommendations on the test articles with cross responses, and also with close rocking modes? Yeah, this is, I think, one of the primary advantages to doing some kind of automatic notching, because you can define a automatic notch on a cross-axis response. This is possible. However, Because the cross-axis response is a function of the input axis of excitation, we can limit that as much as possible, but there may be a point where you cannot remove any more energy to define that cross-axis notch. And this is where pre-test analysis or pre-testing comes really, really into play. The low-level test that you perform before is going to be very informative in predicting the higher level both cross-axis responses and lateral modes. But also, you can try to notch them out at lower levels to see how well your drive responds to this. And to give you an idea of this, I'll go back to sharing my screen. Screen 2. Share. If we look at the post-test from this one we just ran, and we take a look at the drive. Okay, this is the drive output. This is the voltage that we're putting out to the shaker. And this has a noise floor. You know, we're looking at we have about 3.5 volt range peak, or I'm sorry, we have 10 volt range peak and about 3.5 volts range RMS. So we can see at maximum, we only got to about 0.36 volts. This is where we drove the notch downward in response to our limit. So if this were a cross-axis response and the cross-axis response error was higher than the in-axis response, you would suddenly switch over to the cross-axis response. And if you can't cut out any more drive in order to reduce that input, you're going to have a test abort, or you're essentially going to have an uncontrolled system. So this is what I would look at. I would look at the voltages put out by your drive signal to your shaker. I would do a pre-test analysis with the scaled limits for your cross-axis, and then try to determine whether or not those will be adequate to slow down the inertia of the system, you know, throughout that cross-axis response. But that's a great question. I think Nicolay asked that. Appreciate that. He also said in the force limiting equation, defining limiting force. Oh, this is for PSD. We should include the total mass above the force cell. Yes, you definitely, when you're defining this, you have to assume that your force ring and even the hardware, even essentially the bolts, everything above that system has to be taken into account. And this includes accelerometer cabling. It includes test harnesses that might go to your, like umbilicals that might go to the test article. All that has to be considered. And when I very first, I'll do this sharing again. Sorry, I'm bouncing back and forth. During the very first exploratory sweep, this is where you can use your in-axis force. So we'll take a reference of the control. The control channel was input excitation was 0.1 G. So then we look at our in-axis force. This is our transfer function. So this 8.9 pounds that I'm seeing here, or around 9 pounds, it kind of hovers. And if I went down to 5 hertz, this would be much more accurate, by the way. Looking down here in the rigid body mode is where you're going to want to account for that. So like Bill said, you have different ranges. You have different responses at various ranges. So if your test article is 1,000 pounds and you're using a higher portion of your force input, you're probably going to want to calibrate those sensitivities to match whatever the input force is down here. So if this is a 4 kilonewton sensor, for instance, that I'm using here, and I have about 8 kilonewton range in the force Z before I preload it. So once I preload it, I only have as much headroom as I have actually preloaded. I needed to take a look at this at the low frequencies, do the transfer function from a low-level input, and then adjust the sensitivities accordingly to include the force ring, the unit, the cabling, the hardware, and everything. And I use all those in the calculation to determine the sensitivity. If you do that before you actually run a full-level test with a mass mockup, you don't even need your actual test article. You can use a mass mockup to predict this. You will get very, very accurate results throughout the entire sweep. And when you do limit to some very high level, it'll be much more likely to be accurate. Then I have a question here from He Huang Yun. This is he said, what is the maximum channels of an M plus P controller? We can actually run hundreds of channels for this. So in this example, you know, my marketing versus reality example in the beginning, where we had this 32 force sensors or so, that would account for just the X and Y would account for 32 or 64 channels before we even start doing the force summing with an additional 32 channels. So you could define like a 250 channel system, for instance, that could operate that type of test, and we can calculate those forces and the moments together using that system. There's another question from Nikolai here, and I think Bill, you would probably
I can take this one.
Take that one. Thank you.
Yeah, what Nikolai asked is what are the pros and cons of using dynamometers based on a small number of cells, 4 at the corners or 6 in a ring, over using force cells under each interface point. Okay, for example, 8-inch or 15-inch spacecraft adapters, there's 12 to 24 bolts. Hence, it is feasible to use force cell under each bolt. I think this goes back, Nikolai, to really a lot of times the bolts that you might have available are not suitable to preload at the high preload levels of 70% of the full scale range of the sensor. So I would say, as we talked about the preload, you know, going through each individual, you know, mounting point, it might be that you're not able to really realize the actual recommended preload. So you compromise linearity, tensile and compressive capability, as well as shear force handling. So that would be one of the concerns. Obviously, the channel count gets a lot bigger. Okay, so you need a lot more channels if you go under each bolt. If you go just 4 or 6 in a ring, lower channel count, you use the exact mounting hardware from the manufacturer. You get the high preload, and then you mount on top of the vibration fixture. So I think that's probably the pros and cons associated with it. Hope that answered it. If not, Nikolai, just send me another email and we can talk privately.
Bill, can't a dynamometer give you kind of like local response dynamics too? So you may have the dynamics of the entire system, which includes all the dynamometers, but if you have a system which is sensitive to certain portions, can't you use that one dynamometer to help define that energy?
Yeah, absolutely. I mean, that's a lot of times used as you might build a dynamometer under each mounting point. Say we're doing a project now with like 4 mounting points of a satellite. So each one is getting a dynamometer. And so you have the ability to do local forces and moments as well as global. So absolutely. Well, I think we're out of time here. And I think that very good questions. We'd like to thank everybody for joining the webinar. And as I said, we'll send the link out to the video and we'll follow in a follow-up email. And if there's any further questions, just send them in, you know, to myself or Dale, and we'd be happy to answer anything further. In that regard, everyone have a very good day. Dale, any final words?
No, just thanks for joining.
Great. Okay, everyone, have a good day. Take care. Bye now.